recording. Okay, welcome. Let's see here. Reminder. Oh, I changed my pen last class, but now I want to, I don't know. I like it thicker. I know it's not as easy to read, but looks a little bit nicer, I think. Reminder, no labs in the first week of classes. That's for any labs, so don't worry. We need to get through some material before we can actually get into any labs. So labs, I'll also make a note here, labs will be pre-recorded for you to watch on your own time. Maybe I should say watch and work through. On your own time. Okay. That's just a reminder from last day. Okay, so what I wanted to do was I wanted to just do a quick, not quick, but just do a brief refresher of Stat 230. Specifically, I want to focus on hypothesis testing today, and then we'll pick up next week with regression. We'll start with where we kind of reviewing what we did in regression, because I know, because you were mostly with me, that we didn't have a ton of time left over to work through regression. So I pretty much just want to do that section all over again, but go a little bit deeper and that kind of fun stuff. So I'll save regression for next week, but for today, I just want to review hypothesis testing. Okay, and so kind of Stat 230 review, specifically hypothesis testing. Today. Okay. So there is no textbook. I'm trying to find a textbook that kind of does what I want to do, but I haven't found one, especially because I want it to be free for you guys. And so, because I think it's just a good benchmark for me to work towards if we're just trying to use free textbooks. I know that you guys are probably okay buying a textbook, but that's not the point. The point is I want to try to work through free textbooks. So yeah, so as long as we don't have a textbook, just the notes that we write today, everything I say, that is what you are to focus on. So that's good. Yeah. Yeah. But yeah, I'm trying to find these textbooks and they're just not quite right. So I might end up just writing my own textbook. Yikes. But I have some notes that I can kind of go off of. So today I want to focus on just a quick overview of hypothesis testing. Remember, there's so many different types of hypothesis tests that we can do, and we only really touched on a few, the key ones, mind you, okay? But we can do hypothesis testing, you know, for many scenarios, okay? And so let's start with just reviewing the steps of hypothesis testing in general, okay? And so I'm going to introduce a couple of pre-steps that you would have to do before the 1, 2, 3, 4 steps that we talked about last term. Okay, and so just as a reminder, so the first thing you're going to do is identify the type of question. Okay. So identify the type of question. Okay. Easier said than done, right? Often that's the hardest part of doing any hypothesis testing, is just figuring out, well, what type of hypothesis should I run? Can I run here? Okay, and so for us, we've seen two main types of hypothesis testing: one for categorical data, that's where we started, and one for numerical data. And so for categorical data, right, we're testing proportions. Oh, sorry, guys. Steve's not here today. Yeah. No worries. No. Joint office fun here. Everyone just comes in looking for Steve. Everyone wants Steve. Yeah, I know. Anyways, so if we have categorical data, then we're testing proportions typically. Okay, so for categorical data, categorical variables, we test proportions. Okay. Typically, right? We can have one proportion or we can have two proportions, right? So we have seen things like, now this is where things get a little crazy, right? I am going to start referring to the types of questions mainly by their null hypothesis. Ugh. Oh my gosh, are you guys ready for that or what? I know you are. Okay, so we can have, and maybe I'll start by highlighting here. And maybe I should say, maybe test the proportions. Okay, so for one sample, we test the null hypothesis that P is equal to some P naught. Okay, is the population proportion, is it equivalent to some hypothesized proportion P naught, right? Or if we have two samples, we tested how P1 relates to P2, specifically if they're equal to each other or not, right? So then we had P1 is equal to P2, or P1 minus P2 equals 0. Yeah. What could we do as a follow-up here that we didn't do last term that we might consider this term, right? We might consider P1 minus P2 equal to something other than 0, right? So that's another thing that we can explore, right? What happens if we want to test if the difference is equal to something other than 0, 0.1, 0.2, right? Remember, we're talking about a difference in proportions. Proportions, remember, are between 0 and 1. And so a difference in proportion of 0.1 would be the same as 10%. Right, so proportions are typically very small values, right, because they're focused between 0 and 1. So here, this difference would have to be between typically 0 and 1 as well, okay? So things to consider here. Maybe I'll say this term. We will also consider testing against values other than 0. We will also consider testing against values other than 0. Okay. That's an option. Okay, we have to work it a little bit differently, but nothing major. In fact, we're going to be leveraging software for most of these tests now, right? Because you did them all by hand and you understand kind of, you know, what is involved. But for the most part, we're going to use R to do these calculations. I was considering a textbook that also introduces Python, which might be really fun, but I worry that it would be a little bit confusing in the beginning, but I think it might be a good introduction to Python as well. So I'm kind of playing around with that, those ideas. I have big ideas, big ideas. Exactly, right? This can be a safe space where we try Python without telling anyone. How about that? That's what I want as well. Yeah. Let's do it. Okay. I love your guys' enthusiasm. Okay. Yeah. Okay, so well, that's great. I love that you guys are so into trying it, because I think it would be really fun, and it's nice to see kind of the side by side. Yeah, well, so the thing about Python is so I haven't personally worked in Python, but the reason I'm not scared of Python is because I know R, and R is harder. I know it's harder. And so, but of course, it's good to be able to run both and feel comfortable in both. So that's why I want to give that to you, something I didn't have, but I want to gift it to you. How about that? Yeah, for big data especially, Python is the way to go. So I think it's a good thing. Are you guys using Python in any other courses, or is everyone just kind of, nope? Oh, which one? Who's using Python? Nope. Oh, maybe it's a no. No. Oh, look at you go. Use it on your own. Yeah, I think, okay, so you guys are you're teaching yourselves. Well, this will be a safe space where we can try it out together. How about that? We're going to focus on R, but yeah, okay, that sounds great. Now I'm excited because it's been on my to learn list for so long, and I keep pushing it off, and now it's time. How about that? Okay, so where was I with the proportions? Okay, so if we have one sample of proportions, we can compare it to some value. That's pretty rare that we have to do that. Usually we have two samples of proportions, and we want to compare them to each other. Are they the same as each other? Are they different from each other? And then as soon as we have more than, well, I'm going to have to try it now. I should never have mentioned it, but no, I think it's good. Oh, while I'll keep talking about proportions and stuff later, but while we're on the subject of kind of things to do, are you guys using Git at all in any courses? Nope. Okay, because that's another thing that I think we should be doing, just for version control. So Git for version control. I get the feeling that the other courses, and I'm talking about other courses using it. If you're using it on your own, then that's great. But are any other courses using it for you guys? No? Okay. Then that might be a good thing to get you guys set up with, just so it's not so scary when you go out into the real world. So Git is version controller. How we are going to use it is, you might have heard of GitHub. right? And I'll try to incorporate some GitHub as well. But Git in general is version control. So for example, it's really useful when you're running code. So what you would do is you would yeah, exactly. So what you do is you commit your code, and then I know what got into me. I have no idea. I'm like, Python and Git and this and that. And so if your code was running, then that's good. You want to commit that. And then if you make a change and it's not working anymore, and maybe what you've found is you've made too many changes, you can't keep track, then Git will tell you where the changes are, and it'll help you fix those bugs a little bit quicker. Also, if you're trying something new that you're not sure if it's going to work or not, then you can always kind of commit the one that's working and then kind of branch off and make changes. And if it's not working, then you would go back to the one where you started, where it was working. Okay, so it's going to take a little bit of time to get it set up, but I think what you'll find is it can be really useful. Or sometimes you might say, oh, I wish I'd been using Git. I didn't. And that's how we learn, right? And so, okay. So far, I've combined two different textbooks in my mind, so we'll see where that gets us to. But I think this is a good setup. Okay, so hypothesis testing, categorical variables, focusing on categorical variables for now, and then moving to numerical variables. But let's just get a lay of the land here. So for two samples, we are comparing how do these two proportions compare specifically to each other. Are they the same or not, right? And then we can also check for some other difference, right? And so, so we'll consider that as well. But we're going to do that with software. We're not going to do that by hand anymore, okay? If we have more than two samples, shoot, I'm drawing a blank on the chi-squared. There's a couple of different chi-squared tests that we can do. So there's a chi-squared test. I went into this class and I was like, oh yeah, I can do this in my sleep. And now I'm drawing a blank here. We did chi-squared test for independence, but also, shoot. I'm going to cheat and just leave it as chi-squared test for now, right? Various types. How about that? Because I'm completely drawing a blank, but that's okay. I'll come back to it. So probably another day once we get back there. Okay, but for more than two samples, we would use a chi-squared test, and there are different types, right? There's, you know, you have multiple proportions, more than two proportions, and you want to compare them. How do they compare to some hypothesized proportion, or how do they compare to each other? That type of thing. And so for more than two samples, we use a chi-squared test. And now we're going to move to numerical variables. So for numerical variables, we typically, test the means. I'll do proportions. Typically it's plural, right? It's pretty boring to take one sample and compare it to a number, right? That's kind of where we start. but that's not typically what we're doing, right? We have two groups. How do male consumers compare to female consumers, for example, for their average spend amounts, that type of thing. And so, yeah, so for numerical variables, we can test other things, and there are other tests to run, but typically we test the means, right? And so for one sample, we tested the null hypothesis that mu is equal to some hypothesized mean mu naught. Okay. For two samples, we tested the null hypothesis that mu1 is equal to mu2, or mu1 minus mu2 equals 0. Okay. And of course, we can tweak that using. We can also consider testing against values other than 0. Now, for means, it's less common that we would do anything other than 0, because typically we want to compare the two groups, right? And so are they the same or are they not the same, right? And so typically that's what we want to do. I'll show you how to change it, but typically we are testing more against 0 than anything else. Okay. And more than two samples, we use an ANOVA. Okay. Which tests the null hypothesis that mu1 is equal to mu2, which is equal to all the way to mu k is equal to, oh my gosh, no, not equal to 0, there. Mu1 is equal to mu2, which is equal to mu, blah, blah, blah. All the mu's are the same, versus the alternative hypothesis in this case, so for an ANOVA, is that at least one mu I is not the same as the other mu's. Okay, so at least one mu I does not equal mu j. So we're not specifying, but at least one of these is different from one or more of the others. Okay, and so all this does, the ANOVA does, is it just peeks in there and says, hey, is anyone different in there? Right. And if we reject the null hypothesis, then what that's saying is that, yes, there is a chunk in there that is different from the rest of the means. Okay. We can do the same thing for lots of other values, but for now, we've only seen the ANOVA for means. Okay. I'm pretty sure. Can't remember. Honestly, but we'll use the ANOVA quite a bit for regression, okay? Which is slopes, right? Is a slope different from 0 in this case? Okay, that's where I got the 0 from. Okay, so where were we? I think that's all the hypothesis tests that we did last term, and that's what I want to focus on today. But there are also things that we can do. We can test, is the correlation significantly different from 0, right? Correlation, right, refers to the strength and the direction of a linear relationship, and a correlation of 0 means that there's no relationship. Right. And so if I'm testing whether the correlation is significantly different from 0, what am I testing? I'm really testing whether there is a relationship or not. Right. I can test if the slope of a linear regression is significantly different from 0. Right. A slope of 0 means there's nothing going on. which of course is related to the correlation. But there's all kinds of hypothesis tests that we can do and that we will do, right? But for now, I just want to remind you of all the ones that we know, okay? So identify the type of question, which really is rooted in what type of variable do I have, right? Do I have a categorical variable or do I have a numerical variable, right? And then that'll kind of set me on the path of what I can and cannot do. Okay? So the first thing we do is identify the type of question. The second thing we do kind of before we actually start the hypothesis testing process is we have to check the assumptions. Sometimes I use it as kind of a sub step before my actual hypothesis testing, but either way, we have to check the assumptions. Now, this term, I'm going to focus a lot more on checking the assumptions because typically we check the assumptions using graphs and using numerical summaries and stuff like that. So we're going to leverage that a lot more. Last term, what we did, we checked the assumptions pretty rigorously for proportions, right? We had to make sure that I have at least 10 successes, 10 failures, all that. Was my sample randomly selected, right? And do I have less than 10% of the population? All those fun things. Whereas for the means questions, right, when we got into testing numerical data, we pretty much just assumed that we were allowed to do it. So this term, I want to go a little bit deeper and I want to look at, okay, well, when are some of the times we can't assume that we have a normal distribution, for example, and what do we do then, right? There are, of course, solutions, things that we can do to deal with that. And so that's what I want to introduce you to. Okay. And so check the assumptions, or check that the assumptions for inference are satisfied. Yeah. I'm going to leave it there for now because depending on what type of test I'm doing, right, there are different assumptions. But pretty much by the end of this term, what I want to be able to do is tell you that, okay, here are the assumptions for a test, and here's the null hypothesis, and here is the test statistic, right? Or how you achieve the test statistic using software. And that's going to be all that you need, right? Because you know already that if the P is small enough, so if the P is low, the null hypothesis must go, right? So then, okay, if you have a small enough P value, you can reject the null hypothesis in favor of the alternative hypothesis, right? So we are assuming that you know all that already, right? And so we can kind of jump into it, right? And so by the end, right, I want you to be able to research a method, and I'm not going to make you do it, but I want you in real life to be able to look it up and say, okay, what are my assumptions? So I know what to check. And then how do I actually do the test? And what is my null hypothesis? What am I testing here? Okay, and those would be all the things that you need in order to do a hypothesis test of any kind. Okay. And so the tools that we developed in Stat 230, those are really broad, and they're going to cover a lot of scenarios. So many scenarios that you'll come across, right? But there might be other scenarios where we might need a different test, right? And so that's where I want to build you guys up to. Okay. So you have to check that the assumptions for inference are satisfied. I'm going to leave it at that. Okay. And then once the assumptions are satisfied, then step one is to state the hypotheses. Right? So far, so good, right? As long as you know what the null and the alternative hypotheses are, then you're good to go, right? Then you know what you're testing and you know what you're testing against, okay? And the null hypothesis, remember, the null hypothesis is a statement of no change, right? It's going to be your default until you have proof otherwise. So the null hypothesis is always a statement of no change until you have proof otherwise. That's when you can reject the null hypothesis in favor of the alternative hypothesis, right? But the null hypothesis is the one that we have to assume before we can draw any conclusions. So in hypothesis testing, and maybe I should keep this until you have proof otherwise. I'm gonna delete that here just briefly. Because I've got a better place to put it. So it's a statement of no change. Sometimes that makes sense to you, sometimes it doesn't, that's okay. There's really no other way to say it though. So it's a statement of no change. Is the mean equal to 50 or is it not equal to 50? Or is it less than 50? Is it greater than 50? We do I'll say all our hypothesis testing assuming the null hypothesis is true okay? So just keep that in mind, right? We're doing all our testing, assuming the null hypothesis is true, okay? And we only reject the null hypothesis if there's enough evidence against it. We only reject H0 if there is enough evidence against it. Which is really meaning a small enough p-value, right? So that's really what it's saying is we get a small enough p-value. Oops. Okay. So that's just something to keep in mind, right? We have to state our hypotheses because that's our jumping off point, things we're assuming from the get-go, okay? And then we do our test assuming the null hypothesis is true until we find a p-value that's small enough, okay? Then we can reject the null hypothesis. Now, I'm gonna talk more about the p-value later, so don't worry if that is feeling a little cloudy still. The p-value is one of those things that at this point, you know that you should know what the p-value is, but it probably still feels a little bit kind of out there. Oh, if it's small enough, then I reject H0. That's all you've probably remembered now, right? But I want to start to develop kind of this more intuitive understanding of the p-value, okay? So hopefully we'll get there. And it's one of those things, I can't remember if I told you guys, but when I took my Stat 230, kind of a long time ago now, but still, I remember it wasn't until I studied for the final when I had kind of seen all the material and I kind of had that overview that I was like, oh, I get it now, right? And so you will have a moment, if you haven't already, that's fine. you're going to have a moment where you kind of have this overview and you're like, oh, well, that's not hard. Well, I know you might be thinking, Emily, you're off your rocker. It's all hard. It is. But one day you'll have that eureka moment where it all lights up and you understand it. I promise. Big promise to make. Okay, so step 2 is to do the test, which is really calculate the test statistic. Now, depending on what type of problem we have, right, that might be calculate a Z-score if you have a proportion, 2 or fewer proportions, might be calculating a chi-squared statistic, might be calculating a T, might be running an ANOVA, so an F statistic, right? And so calculate the F statistic. Sorry, the test statistic. The F statistic is a test statistic. Calculate the test statistic, which could be a Z test, a T test, a chi-squared test, an F test. And the list goes on and on and on. And we're going to add more tests to that list. But what you'll find is things like the t-test, for example, can be applied to many other scenarios. Like when we're testing the correlation, for example, then we do a t-test. When we're testing the slopes, we do a t-test again. And the individual slopes, we can do a t-test. So the t-test specifically and the f-test, and even the chi-squared, but mostly the t and the f, those are going to come back, right, for other scenarios, but then you'll at least be familiar with what you do. Now, for this course now, we're not going to calculate these test statistics. We are going to use software to calculate these. Oops. Use software. So we're not going to calculate these by hand anymore. We're going to use software and we're going to run these tests, which will also give us the p-value at the same time. Okay, so step 2, now, yeah, you're done with that. Yeah. No one wants to calculate those. It's good to appreciate what software is doing for you, but in real life, no, we're just going to run the test. And I say just, but the hardest part is going to be identifying what's appropriate, right? What tests should I be running? And then the software will usually do step 2 and 3 together, find the p-value. Okay, so usually software will output the test statistic along with the p-value, of course. Why would you want just a test statistic? That makes no sense. You're finding it to find the p-value, right? And so software will output the test statistic along with the p-value at the same time. So we can kind of start to morph step 2 and step 3 into running the test, right? So just put it into software, and I make that sound easier than it is, potentially. But that's just going to become one step now, right? You still have to have a good handle on your hypotheses, right? So your null hypothesis, your alternative hypothesis, but there's very few calculations that you need to do. Then you run the test, right? And so once you run the test, you have the p-value. Now it's up to you again, right? So it's kind of a back to you, now interpret it. Okay? So we're going to focus way more on the interpretation of the p-value than anything else. In fact, I'm completely ignoring the confidence interval of it all, but usually if you're running software, and I say it broadly, but usually it'll produce the confidence interval as well. It's like, oh, and here's another thing you might want, right? And it just gives it all to you. Right? So find the p-value. Depending on the test, the p-value comes from different distributions, right? It might come from the Z distribution, it might come from the T distribution, it might come from a chi-squared distribution, it might come from an F distribution, and there are many other distributions that we can talk about, right? But for now, depending on the test that we ran, right, software will put out the appropriate p-value, okay? Depending on the test we ran in step 2, software will output the appropriate p-value. Okay? The appropriate p-value. Okay, let's do a little refresher on what the p-value is. And what I think you'll find is now that we're talking about this again, right? You've already seen this, and even if it didn't make sense at the time, right? The more you hear it, like I said, one of these days it's going to click in. Okay, so I guess it's my job to just say it over and over and over and over again. I try to say it in different ways, but sometimes there's only one way to say it. But so the definition of the p-value, and I guess I shouldn't call it a definition because it's just kind of off the top of my head. But the p-value is the probability of something as extreme or more extreme than what happened in your sample, assuming that the null hypothesis is true. Okay, so it's the probability that something as extreme or more extreme as what happened in your sample the probability that something as extreme or more extreme as what happened in your sample happens assuming the null hypothesis is true. There's a lot of happenings in here. Happens assuming the null hypothesis is true. Okay. So picking it apart a little bit, the as extreme or more extreme, that's what makes it the area in the tail, right? And so we can have just one tail that we're interested in, or potentially both tails that we're interested in. As a default, we consider the two-sided test, right? So just both tails. So if we go back to basics here, and if my null hypothesis is, so for example, if my null hypothesis is that mu is equal to 30, just picking a random number doesn't matter, okay? My null hypothesis is that the population mean is equal to 30, because that's the easiest thing to wrap your head around. So what we do then is we assume that the mean is 30. So then we have this normal distribution because we check the assumptions and it all checks out. So the mean is 30. That's what we assume. Okay. So we have this distribution that's centered on 30 with some degrees of freedom. Doesn't matter. Let's say 50. It really doesn't matter. It has the same shape, right? So I shouldn't say the degrees of freedom don't matter. They don't matter for this example, okay? So now, so if our null hypothesis is that mu is equal to 30, then we assume that we're pulling from some distribution that looks like this. We understand that whatever sample mean I pull should hover around 30, and depending on what the standard deviation is, right, I might be further away from 30, and that's where the t-test comes in, right? It tells us how far from 30 I was, okay? And so here, if I put my, if I land up here, x bar is equal to 41, depending on what the standard deviation is, right? If the standard deviation is huge, what if it's 100? Then 41 is not that different from 30, right? And so that would determine where it would fall here. And that's why we need that t-test, right? To standardize how far the mean is from the hypothesized mean, okay? And so here, this area is the probability, right? Because it's an area under the curve, is a probability of something as extreme or more extreme than what we saw, okay? And so here, this is the p-value. So this is the one-sided p-value. So something as extreme or more extreme. That's what makes it the area in the tail. Area in the tail. So what we established last term was, okay, we shouldn't really be using one-sided tests, because what we find is, for example, if I had said that HA, so the alternative hypothesis is that mu is less than 30. I'm going to erase this because it doesn't apply. But if this was my alternative hypothesis, even if 41 is significantly more than 30, I can't use it because I went into this only wanting to know whether the mean was less than 30. Right. So even if this became, significantly larger than 30, I can't use it. Okay, so that's why we should only use, unless it's a rare circumstance where, it's a problem that's asking you to use a one-sided test. But in general, we should default to a not equal to. Okay. So in that case, what we do is, okay, X bar happened up in the higher end, but it could just as well, we're allowing it to happen on the lower end as well. So then we kind of multiply our p-value by 2. Of course, software is going to do that for us, right? And so I'm just seeing what time we go till, and I actually don't know. Okay, good. I think we have more time. Yeah, we go till, great. Good, because I thought I was out of time and that would be really bad. I have so much more to say. Good, great. Okay, so the one-sided p-value, we multiply it by 2, but software would already do that for us, right? And so, so what we need to have a really good handle on is the definition of the p-value. Right. And so it's the probability, and that's what makes it the area under the curve. right? That's something as extreme or more extreme, and that's what makes it the area in the tail, as what happened in your sample, right? What's the probability of that happening, assuming that mu is equal to 30, right? What's the probability of seeing a mean of 41, assuming that the population mean is actually 30, right? If that p-value is small enough, right? If that probability is small enough, then I have enough evidence to reject H0, right? Because then it seems unlikely that I pulled from a population where the mean was 30. It seems more likely that I pulled from a population where the mean is not 30. We're not committing to any number. We're just saying, okay, it's actually more likely that I pulled from a population where the mean is not 30. That's all I know. And that's okay. Okay. And so that's the idea with the conclusion that we draw. And that's what's really hard to kind of instill in Stat 230, because we go through all these tests and it's not until you've had that overview that we can talk about it in these broad terms. And if you flip back through your notes, you'll see that I said the exact same thing in Stat 230, but you hadn't seen everything that you've seen so far at that point. So what I'm hoping is if I say it again, then it'll start to kind of click in. Okay, so the last step, step 4, is your conclusion. And remember, I kind of break up your conclusion into 3 parts, and your conclusion is typically worth quite a few marks, right? And so and the reason for that is because doing the test statistic, so calculating the test statistic, if you're doing it by hand and finding the p-value, those are all eventually going to be coming from software, right? And so that's not worth a whole lot. Anyone can run that, anyone can produce that output. But your job, the most important thing is step 1, setting up your null and alternative hypotheses in a way that people can understand, and then jump forward to step 4, because the actual computation that you're doing is relatively easy, right? That's not the hard part. The hard part is going to be the conclusion. So what kind of conclusion can you draw here? So for your conclusion, right, remember, if the p-value is small enough, which means is the same as saying less than the alpha level. And the alpha level is the significance level. All these same terminologies, synonyms. So the alpha level, so if the p-value is small enough, which we determine by checking it against the alpha level, so the significance level, we have enough evidence to reject H0 in favor of HA. Okay. So I'm going to be really picky, admittedly, really picky about your conclusions this term. Okay, I was picky last term too, so that's nothing new, but I'm going to be extra picky. Okay, because what do you have to do? You have to support every statement that you make. You have to support it. Okay, and so what are you going to do? You're going to tell me what the p-value is, right? You're going to compare it to the alpha level. You're going to tell me what it is, right? It's not just enough to say, oh, the p-value is less than the alpha level, so I reject H0. No, Okay, you have to say something like, since the p-value is 0.0001, right, or less than 0.0001, right, it is also less than the alpha level, which I'm using 0.05, for example, right? You have to back it up with the numbers so that people can be convinced, right? That means I have enough evidence to reject H0 in favor of HA. Okay, and so your conclusion is going to have 3 parts, right? So the first part of your conclusion is compare your p-value to the alpha level, right? Giving numbers as well. Compare the p-value to the alpha level. Always include values for the p-value and the alpha level. Okay, so what I mean by that, for example, is since the p-value of 0.064, how about this? 0.0064, I want to reject H0. Just feels better, you know? Since the p-value of 0.0064 completely made up is less than the alpha level of 0.05, okay, we have enough evidence to reject H0. We have enough evidence to reject H0 in favor of HA. Okay. So I want you to compare the p-value to the alpha level. I know a lot of you are doing it already, and I'm so proud of you, but now I'm really going to come down hard. Okay, so since the p-value of 0.064 is less than the alpha level of 0.05, the idea being someone should be able to sit down and read this and not have to look at the output, right? They might not even care about these numbers, but you have to support your statements, right? So a typical scenario is, you know, you work for a firm or you work for, you know, some institution, right? And they just want the information. We're the workhorses that give the information, and there's lots more that we've done that we don't get to show off, right? But there's a lot going on that, oh yeah, but all people really care about is, do I reject H0 or not? Right, and so that's kind of disappointing, but what you want to do is you want to make sure that you cover your bases, and you want to highlight that, okay, well, because this value is less than the alpha level of 0.05, which I'm using, which can change, right? It could be 0.1 or 0.01, depending on the severity of rejecting H0, which we'll talk more about type 1 and type 2 errors, but it's basically a review from last day, but we'll save it for next week probably. Or you can just review it on your own. But depending on the severity of rejecting H0 when we shouldn't have, right? That's going to determine what the alpha level is. But in general, we use an alpha level of 0.05 as a default, right? Depending on what industry you're in, it might be different, but in most of our industries, 0.05 is the default. Okay, I say our as in financial data and stuff like that. Whereas if you're working in, I can't stop talking about it. If you're working in COVID vaccines, for example, you want to be really, really, really sure that that thing's working, right? not just not working 5% of the time, that's not good enough, right? You wouldn't feel comfortable reporting that. Oh yeah, you can go ahead and use it. Well, it doesn't work 5% of the time, but that's no big deal, right? And so, right, well, we're not sure 5% of the time, that's not good enough, right? You want to be really sure of results like that. And so then you would decrease your alpha level, right? Make it harder to reject H naught. Okay, so that's the first step. The second part of your conclusion is if the p-value is less than the alpha level, okay, and so if, and I'm going to use notation here, if the p-value is less than the alpha level, you have enough evidence. You have enough evidence to reject H naught in favor of HA. Oops. Okay. Whereas if the p-value is not less than the alpha level, so if it's greater than the alpha level, if the p-value, I want to use an exclamation mark equal to or less than to say not equal to, but I'm not going to do that, is greater than or equal to, you know what, I'm not going to use the equal to, there, is greater than the alpha level. Or you can kind of say, or not less than. Usually that's how I formulate it, is if it's less than the alpha level, then you can reject H naught. If it's not less than the alpha level, you do not have enough evidence to reject H naught. So then you do not have enough evidence to reject H naught. Okay. I summarize this step of the conclusion as your conclusion in terms of H naught. Conclusion in terms of H naught. Do you have enough evidence to reject it or don't you? Okay, whereas here, I would summarize this as just compare the p-value, which I said already, but it's nice to have kind of a broader category for each of these. Compare the p-value to the alpha level, right? Second step is your conclusion in terms of H naught, right? Because we assumed the null hypothesis was true in this whole test, right? So now you have enough evidence to reject H naught, or you do not have enough evidence to reject H naught. I do not want to see any mention of accepting H naught or not accepting H naught. I don't want to see the word accept anywhere. Okay. Note. I do not want to see the word accept anywhere. Okay. Why is that? Why am I so hung up on that? Because there's an alpha level chance that I'm wrong, right? Technically a p-value chance, but I set out doing my test allowing for an alpha level probability of being wrong. Okay. Okay. This is because we started doing this test, or we conducted this test with an understanding that there is an alpha level probability of being wrong. Okay, so this is because we conducted this test with the understanding that I am allowing an alpha level probability of being wrong. Okay, if I reject H naught, right, there is still a 5% chance because there's a p-value chance of being wrong, but I'm still allowing a 5% chance of being wrong, right? Maybe it did come from a population where the mean is 30, right? We just happen to see a very large mean, right? That can happen. It happens with a p-value probability. Now the p-value might be really, really small, but the idea is that, okay, I entered this test and I said from the get-go, I'm going to allow a 5% probability. So an alpha level of 0.05, which is the default, I'm going to allow a 5% probability of being wrong. I'm okay with that. I'm okay with being wrong 5% of the time. Okay, I'm okay with feeling like I'm right 95% of the time. Right, that's the trade-off. It's pretty good. Okay. Okay, so so we conduct the test with the understanding that, okay, I'm allowing an alpha level probability of being wrong. Okay, so that's why I don't want to see the word accept anywhere. You can't accept anything. There's always a chance that you're wrong. Okay, and that's what we need to do a really good job of emphasizing is that, oh, okay, well, here's what we found, but here's the probability that we're wrong too, right? We can't pretend to know everything, and we shouldn't. We don't, right? And then finally, the part of the conclusion that people like to forget, or probably don't like to forget, but it's probably the most important part of our conclusion, is translating what does rejecting H naught mean in terms of the question, right? And so the third part of our conclusion is the conclusion state the conclusion from part 2 in terms of the question. Right? What does it mean to reject H naught in this case? Is the mean significantly different from 30? What does that mean? What is it, 30 miles per gallon? Maybe if we're talking about fuel consumption, that seems high, but who knows, right? More than 30 meters on average, I don't know. All these different things that we can consider, right? And so here, we'll call this the conclusion in terms of the question. Okay, that's the one that people tend to forget because you put so much time and effort into, okay, finding your test statistic, then finding your p-value, and then interpreting your p-value. Is it small enough? Comparing it to the alpha level. What does that mean? Can I reject H naught? Right, and so, and then you forget to tell me what it means in terms of the question, which is arguably the reason people are hiring you in the first place, right? Is because they don't want to do this for themselves. So, so you always have to state the conclusion in terms of the question, right? This is the reason we all have jobs. We all have or will have jobs. Because no one wants to do it. No one wants to put their name on the line and say, yep, this is what it means. and it's hard. Okay. Notice that I don't go into specifics, right? It doesn't really matter what type of test I've done, right? Right, in terms of here, I use the one sample mean because it's the easiest one for us to wrap our heads around, right? But that could have been a hypothesis about any of those scenarios that we've seen, right? And so that's what's so nice about hypothesis testing is once you understand these steps and you have a good handle on the steps, and I'm going to include checking the assumptions as well, because that is going to take a bigger role now, okay? But the first thing, if you identify what type of problem you have, you find what are the assumptions for doing that test, what's the null hypothesis for doing that test, and then what's the test statistic, and then you can just kind of roll with it from there, right? So notice how I'm not mentioning any specific tests here or any specific type of data that I need, because this applies to everything that we're going to do, right? And so this is statistics. This is what we're doing here for the most part, right? And it's all going to come back to this, and we might emphasize it more or less, but to have a really good handle on hypothesis testing is going to pay off. Potentially quite literally, it's going to pay off because no one wants to do it. That's why we're here. I feel like that's a pretty good place to end today. So no lab this week, so you're off. I hope you have a great weekend. Let me know if you have any questions, but I'm going to stop the recording here.